Dear spectators, dear audience, we're on air again, and this hour we're going to have a discussion about AI for science and science for AI.
As you may know, Sber is one of the leading tech companies in Russia. Research and innovation is the important tool to build technical advantage. So that's why the company invests a lot into hands-on and fundamental research. Sber supports gifted and talented researchers working in Russia. That's why in 2021 Sber has started the research prize with the overall prize fund of 60 million rubles. Let's take a look at the brief video. Dear audience, dear viewers, let me introduce the moderator for the upcoming discussion, Mr. A.Efimov, the PhD in philosophy, Vice President of Sberbank in charge of research and innovation. He is also in charge of the Department of Engineering and Cybernetics of the National University of Technology and Science, MISIS. Please. Evgeny, hi there. Well, we're supporting the research and science in Russia, but let's talk about science with the researchers who do not need any further introduction because they're widely known and celebrated. Today we have Mr. Stanislav Smirnov, the professor of Geneva University, the professor of Skoltech, a PhD in math, the director for Swiss Center of Mathematics and Theoretical Physics, the researcher and manager of the Faculty of Math and IT of St. Petersburg State University, where he also is a professor. Stanislav is a member of European Swiss Royal Academy of Sciences. He was also awarded with Fields Prize of 2006. Together with us, also we have remotely, Mr. Novoselov, the professor of Manchester University, PhD in physics, the leader of the Revolutionary Research Center for Materials and National University of Singapore, the member of the London Royal Academy of Sciences, the winner of the Nobel Prize in Physics in 2010. Konstantin, welcome.
Вам нужно включить звук. Да, спасибо, что вы с нами сегодня.
Thank you for being with us today. Also with us, Mr. Anokhin, Konstantin Anokhin, professor of Moscow State University, the member of the Russian Academy of Sciences, the director for the University of Future Research of Brain of Moscow State University, also in charge of the lab of neurobiology and memory in Moscow State University. Konstantin, thank you for being with us today. Can you hear us, Konstantin? Okay, while we're fixing a sound, let's talk about the role AI in fundamental research and what fundamental research can give to AI. This is a very essential question. Dr. Kitana, the CEO of Sony in charge of AI, suggested in 2016 that in the near future, the machine that will overcome a range of cognitive limitations will even be able to get the Nobel Prize. The mathematical problem of three bodies, formulated by Isaac Newton in the 18th century, has been unsolved, but it has been partially solved with the AI methods. But who did it? People who wrote the algorithm or the algorithm? There was a very good example of the team of DeepMind, which, thanks to the algorithms of AI, was able to solve the problem of protein. So we'd like to talk to the members of the three disciplines, physics, mathematics, and microbiology. What role AI plays in their research? What are the principal confinements of the application of AI in natural sciences? And what can fundamental science and research give to the breakthrough in AI. There's a range of fundamental disciplines without which it would not be possible to imagine contemporary science, mathematics, neurobiology, physics, because contemporary computations and AI are based on just linear algebra, which is about 150 years old. It's all about physics because, of course, the semiconductors is a material that has been there for 150 years. It's all about researching of natural neural networks, and that's why we need microbiology. So what can fundamental science give for future research for AI? I would like to start with math. Stanislav, every time I think about math and philosophy, I recall this old joke about a university when the rector of the university wanted to find out which faculty spends the most money in the university, because the rector was very frustrated with the physics, department of physics that buys lots of hardware. So he asks the manager in charge asking who spends the least money. He was expecting the mathematicians. Turns out that the least is spent by the philosophers, because they don't even need a trash bin for their drafts. But probably AI, as some sort of supercomputer using the tools of supercomputing now, is being added to mathematical apparatus that's used by those who do mathematical research. We're not the first ones to be speaking about that, because even in the 70s, the laureate of Fields Prize on mathematical logics, Paul Coyne, was saying that computers, sooner or later, will replace mathematicians. In 2018, Stanislav, you were saying that different research groups, for example, at the International Mathematical Congress that's going to be hosting in St. Petersburg next year, are conducting research in that domain. You also mentioned that half of the Euclid's theorems have been done with AI methodologies. So question, how do mathematicians who do pure mathematics are now applying AI? And is there a future of AI when it gets the Fields medal? Okay, I can begin. Let me begin with a joke. Unlike Nobel Prize, there's age for a Fields medal. You have to be no older than 40 years old. AI is older than 40 years old, so it missed the chance. But if we speak with all seriousness, there are two aspects of math where we widely apply AI. One of them being, like for those who do physics, like for physicists, we have a ton of data, and for mathematicians it's even bigger, because we're more interested in older articles, which are 100 years old, for example. And of course, AI help us to find our way in between all of those articles. Even when we began digitizing of the databases with computers, that already made things easier. But there's now search, which is much facilitated with AI, making our lives and work easier. Second point, verification of results. If, for example, a physicist expresses certain hypotheses, it can be tested in a lab. And if the theory corresponds to reality, that theory will not go to a trash bin. For mathematicians, it's a bit different. I mean, again, if a theory is very beautiful, the mathematician will get that theory, but a beautiful theory, from a trash bin and use it. But of course, we need to, prove our theories in math. Euclidean theories are an example here. There's a good example when we had statistical AI like Turing-based logical AI checks our proofs. And there's a lot of progress in that domain. There's a very complex theory and theory of groups, and it's about 200 pages of proof, which has been checked thanks to a logical Turing-based system. Pretty much we can check any sort of proof today, but it needs to be written in a special sort of language, which is similar to programming language, in order to avoid some ambiguities. For example, when I speak a prime number, again, it's 1, 2, 3, 4, etc. But the French start prime numbers with 0. So here's a question. We can write it in a specialized language, and it's a bit more complex. The mathematicians need to learn that. But for prime, the language of primes is a special language, and it's hard for us to transfer the language of primes into a more specialized language. It's about upgrading the NLP, and it's not even easy for humans, because there are humans who write articles so that I don't understand Russian language as much as I try. But there's still a lot of progress, and it's really curious whether AI can, for example, discover new theorems. The mathematicians are always saying that math is very complex, and in about 20 years the theorems will be so long to prove that mathematicians will not be able to invent those theorems. But we have been saying that for 100 years. Still turns out that we have been moving along. There's a lot of progress in many domains. Everybody has known that Poincare hypotheses or Fermat theorems were proven in the last 25 years. So the process is sort of tagging along, but soon the humanity will reach some sort of threshold. And the question is whether AI will be able to help us go beyond that threshold. And that's not even proving theorems, but just discovering those theorems. What's the beginnings of contemporary math and physics? It's that we have discovered certain rules, Tycho Brahe rules of the movement of planets, and Kepler analyzed them just looking with the bare eye, and it has been discovered that actually the movement of planets are not circular but elliptical. And probably we would have been able to discover that quicker thanks to AI. It's actually very surprising that they could do that with an eye, which is bare eye. Newton actually got them from a simple equation. Let's imagine there are some simple rules in physics, same in math, looking for rules in figures and primes. And some of them are too complex for a person to notice. Like, we cannot notice quantum mechanics with our eyes, and we cannot put together quantum mechanics and relativity because it's just too complex for our minds. But AI, when we come to AI, it might be able to notice that. There's no good answer there yet, so we're waiting for the progress. So, if I hear you correctly, mathematics cannot overcome a threshold of the unknown, something that we don't know that we don't know. Unknown, right? I mean, I'm saying that hypothetically there's this unknown that we don't know. Some level of complexity that the person cannot get over. But so far we're going in stride, inventing new hypotheses and theorems. Maybe there's this threshold of complexity in natural sciences, like in physics. For example, some sort of pattern that the person cannot notice in physics. Let me suggest a joke. For example, two bodies gravitating to one another, and depends on the amount of atoms in those bodies, or quarks in those bodies. We cannot visually notice the amount of quarks. Mars is gravitating more than Jupiter because they have different numbers of quarks in them. But AI can notice that if it has enough data. I'm just giving you an example out of blue. Yeah, the next question is a question of correlation. What's the cause? What's the effect? But we are moving to physics here. Konstantin, the faculties of physics in Moscow State University, etc., are beautiful institutions that prepare the best experts for AI. And I believe many of those who are listening to us at the moment have graduated from these faculties because they have been so trained that they can very quickly adopt the methodologies of AI and ML. But another thing is curious here. When AI is being applied to certain branches of theoretical physics, for example, the physicals for particles, it's getting more and more popular. There are over 350 articles released only for the particle physics dedicated to ML. So the interest here is pretty high. Similar is in material sciences. In your interviews, Konstantin, you were saying that neural network helps us to plan the synthesis of new materials, set examples in the virtual world. You're saying that AI is becoming sort of competitor for human who is conducting experiments in a lab. In our previous conversations, yet you were quite skeptical about the ability to granting Nobel Prize to a machine, because the machines and computers are not yet creative and inventful enough. So, in the future, how AI will be applied in physics?
вычислительных методов в экспериментальную
What's the competition in computation there?
или, возможно, какие-то альтернативные
Is there some sort of alternative way to apply more general AI? For example, how physics may find AI that is strong useful? Thanks a lot for the question. Indeed, we have been discussing this matter for so long that I think I have switched my point of view a number of times. That's why I believe that we need to rewind a little bit and understand how we apply AI and how we apply our very own intelligence, human intelligence in physics. Probably the first thing that must be mentioned is that we are applying AI and ML in our daily work, and there are many other groups that do the same on an ongoing basis. We have a ton of projects where application of AI is a tremendous aid. It's an aid to solve practical, hands-on issues and find answers to fundamental questions alike. We need to say here that physicists don't like complex tasks. Generally, what would we call a complex task? As STAS, as defined, this is a task that cannot be described with a beautiful equation. If something is being described with an equation where you would need to write it down, an equation of a half a page length, that means that something is wrong there. We need to keep on digging, keep on thinking. And the class of this sort of tasks, I believe it's pretty broad, and people rarely solve these tasks because we consider that this is just not quote-unquote beautiful. Let me explain how we usually avoid this sort of problems. However, these problems are particularly the branch where AI can help us a lot. Can help us a lot to find patterns and maybe even write that sort of equations. In the end, the physicists must not only create new materials, but to understand fundamental principles of the processes, of the ongoing processes, so that with this knowledge, we would be able to predict the behavior of new structures. So, fundamentally, AI is helping us to predict behaviors, and it may even help to describe with some variables and symbols what is happening in there. As I have said, however, for physicists, the major task is to show a beautiful, delicate, thin representation, slender representation. Let me give you a few examples where AI truly helped us a lot. We're now working to create new catalysts based on semiconductors, and this is the domain, which is very, very complex for a simple mnemonic understanding, and we believe that AI is particularly helpful there. Next, what do we want to get more from AI? As I've said, when physicists get some sort of description of a problem, and when we see that the solution cannot be written down as a slender one-liner, there are two ways to tackle this situation. First, just let it go, saying, well, it's not so beautiful. Second thing is to figure out new sort of language to describe it. And that description, in turn, will allow us to make a complex equation into a slender one-liner. So we take the new system of coordinates, we take a new set of terms for description. And it's always a guesswork to introduce a new function. Introduction of a background function into a Schrödinger equation. Well, that's not on the surface, but as soon as you introduce it, you get some sort of mnemonic rules, which are so much easier to work with. And at the moment, any student of the third year can easily operate with background functions. But in the beginning of last century, the wave function was a very, very disputable point. It was very hard to introduce the wave function. It always shows that the new language is becoming useful, but it takes time to adopt the language. It takes time and effort to make people embrace the language. And it's not the latest, it's not the last sort of language that we will be using for this sort of communication to describe our physical universe. The question is whether AI is capable of suggesting these new languages to show in beautiful terms and equations what is the meaning of the patterns that it can see and notice. We know that these sort of patterns are visible to AI. As for suggesting new language, I believe now we see that we are approaching this, so that new language and AI can create. I mean, AI can create new languages and new descriptors. It's about AlphaFold. It's about describing the protein structure. The entry graphs there have been unified depending on the entry data. And in my opinion, that is a correct way to go. And that is a correct algorithm to not only get ties between input and output parameters, but also finding the correct description for this sort of system. Konstantin, thank you so much. We do observe that we have another guest participating, so let's cross our fingers. We had technical problems. Hopefully they will not persist. Let me say this. Today's subject of our discussion has been inspired by the lecture that was presented at the Sber Neurobiological Institution. Neurobiology inspired machine learning, pretty much, that we're discussing on a daily basis. But is there a two-way street? Can AI help us learn something about our brain? Dr. Kitana noticed the usefulness of application of AI for natural sciences. And I believe there is a more fundamental question there. In your opinion, can AI help us to answer the fundamental questions? How do we think? Or what is consciousness? Maybe other animals have consciousness. Beaver is the first engineer on Earth, but AI can help us find the answer to the question who we are. Why are we the only beings on this planet who can launch spacecrafts or host AI conference? Will AI be able to find us the nature of consciousness? And if the answer is found, who will get the Nobel Prize for that? Yes, Konstantin Anokhin. Thank you very much for the invitation. Albert, you asked many questions, and it's hard to answer all of them briefly. Let me start with the latest one. I believe when the discoveries and results delivered by AI will be at the level of Nobel Prize as granted to people, we believe that they will just stop giving Nobel Prizes at that point. I mean, the domain of research will be moving away from technological applications to creative applications. In the end, we know Nobel Prize for understanding different sorts of protein structures. But as that goes to automation and AI plays a key role there, I believe that it will stop being a subject matter for Nobel Prizes. We will discover new domains in the more murky domains of cognition, where we have not yet been able to apply any sort of algorithms. So we will be making new discoveries in domains where we have not yet been even thinking of applying algorithms and machines, where AI is not even applicable in its variation. We will go into abduction. The researchers are using induction, deduction, and abduction. Induction, I mean, it's when you correct a ton of facts and you make some sort of pattern. Artificial neural networks are very good at this. Deduction is a logical conclusion that can be done by a classical AI, but there's third domain that Einstein called intuition or imagination, you name it. And I believe that the largest achievement in research has been made thanks to intuition, intuitive coverage of many facts, thanks to intuitive coverage of many facts. Einstein used to say that solutions are simple. The hardest part is to find the question. The answers are simple. The hardest thing is to find a question. Having answered your questions about whether AI will be getting Nobel Prize, we believe that humanity will preserve the hardest domain of research. The humanity will be filling its way in the dark, filling the essence of problem. This is intuitive. This intuitive work takes years, and it's very hard to formally describe it. And AI systems that I do know are not equipped to solve abduction tasks. However, tons of things related to research of human intelligence and mind today are getting tremendous boost from AI technologies. That is true. Let me give you an example. When we react to some sort of event in the outside world, there are situations that just matter more to us than others. Sometimes we can create these sort of situations that we will react more actively because they attract most of our cognitive resources. These sort of situations in behavioral researches are called hyperstimuli. For example, if we take a silver seagull and show it a red pencil, a pencil with a red mark that looks like mother's beak, from which the seagull is normally requesting food, the seagull will request to it much stronger, that to the natural beak of the mother. There are a ton of such situations, and people, ethologists, are looking for similar hyperstimuli for human beings. A couple of years ago, in Harvard, in the Margaret Levinstone lab, they have used artificial neural network for that. It was created so that this generative AI-based neural network was synthesizing images out of nothing. But the trick was that it has been estimating how not animals react, I mean the monkey, but the neurons within the brain of a monkey. And the researchers were able to discover, by registering a single activity of a single neuron of visual cortex, having shown a number of images to that neuron, what actually the cell, the neuron in a brain can see. And the images were just unbelievably surprising. Not a single neurophysiologist could have been able to forecast that our cells of visual cortex, single neuron, sees it that way. It's an exceptionally complex way of visual representation when you can actually identify certain indicators. For example, one neuron was able to stitch the images, of the red collar of one monkey and, for example, the caretaker in the cage that feeds the monkey. So we get this visual window to study the fundamental principles of neural cells operations. Another amazing thing for cognition is that a year ago, OpenAI company was using the very same principle to research what neural cells see in deep neural networks. And having applied the same methods of maximization of answers, they've seen that deep layers of neural network, deep network, and the receptor fields in this network behave in the very same odd way, the sort of stitching of fragments of different insignia, yet it's recognizable. Some neurons, they code faces, characters, same as for biological cells. That is happening in an abstract way. I mean, they can code the face and the name of the person stitched to it, like Adolf Hitler, or image of a person based on many photos that were shown to the artificial neural network. Some neurons are coding emotions, emotional expressions, I mean. So, the reason why the neural network that we know does not work like a biological brain in deeper layers, but still it can form cognitive specializations of artificial neurons. Not even neural morph, not even physical, but programmed. Similarly to biological deep network, the answer to the question why it's happening like this is a key to understanding the fundamental patterns of cognitions, even though artificial neural network and biological brain, of course, decode world differently. This is one single example, and there's a ton of them.
The example was really amazing, and I think it's perfectly correlated with what we showed today with the help of Udale. It's a neurocity transformers that generate image based on text. Let me get back to mathematics and let me ask a question to Stanislav. In public speaking, in your speeches, you have numerously mentioned that modern studies in AI and their practical results are ahead of the theory. Oftentimes, once you even said that we are like people who are building trains before thermodynamic laws became discovered. So trains would work, but they would explode sometimes. Physics helps build trains that work and they do not explode. We know that machine learning works, but we can't explain why. At the same time, you have numerously mentioned that mathematical detailization can help us progress in AI in the next 10 years. You said that there is a new science of artificial intelligence becoming available, and as you said, it must be science based on data or maybe a complex of sciences, audio, signal, and other entities. So these new science, and what's the role of AI, and what's the role of mathematics in this new AI? I think it's very important. Yes, I think it's very interesting. As Yogi Bear said, it's difficult to predict, especially it's difficult to predict what's going to happen in the future. And what Konstantin said about the new language, about new functions that are really coded. So some regular definitions are coded with our neurons, but it's so habitual, so normal to us that all the mathematicians and physicists perceive it normally. And there is another great example here, and revolution of Newton and mathematical analysis creation. On top of that, there was another revolution, Fourier revolution, a great scientist. He was a great administrator with Napoleon. He was a governor of Lower Egypt, then the governor of Misr. So when he was studying the equation of thermoconductivity, he was doing a lot of experiments in his governor's office. He would close and open the window and see how temperature was changing. Then he realized that the equation of temperature distribution is going to be much simpler, and it was quite well used back then. It's easier to represent it as a rows of Fourier and as a sort of row of sinuses, like in music, a sum of notes. Back then, it was difficult to understand how it can relate to heat distribution, but back then it was still normal. But it turns out that some things do not apply there, and Fourier basis, in case if you have photos on your cell phone and everything is distributed according to sinuses. It's clear why music should be distributed by notes, but why should images be distributed by sinuses? And then that language was improved, but mathematicians were doing it because of their curiosity. Otto Sternberg came up with the mini waves. It's an analog of sinuses, but it's a local, first zero, then upflow, then a peak, then zero again. And then it was taken by other people and it was turned to perfection, just like encoding data. JPEG is the standard. The majority of pictures on your phone are in JPEG, and it's kind of language for images. And if we speak about regular neural network language now, if you give it an image and if you do not represent it with wavelet, it will represent it this way itself. It will get to it. So we need a new language, but the question is, what do we need? Do we need something that humans can do, or do we want to go further? Do we want to go beyond? And where exactly beyond? Maybe we just don't know the patterns or the laws that we want to discover, or conformities. It's kind of, we're trying to make it, we're just like that analogy that humans first tried to build a plane that flies like a bird, and then they built a plane that flies a different way. But there are some other things in common. Winds are in common, for instance. I have 3 examples here. Let me make one example, the one that's closer to my work, to what I'm doing. For instance, a task. I will show you a screen of a TV set. There it has millions of pixels, 4 millions of pixels, for instance, on a TV set. A part of them will be white, another will be black. And I will ask you, are there more black ones or white ones? It's easy for a human to answer this question. Just like another Konstantin said, that our neurons select information and they have it in visual cortex, and there will be some coefficients of Fourier, and we will see which ones are prevailing, black ones or white ones. But we will say with confidence if there is more white or if there are more black pixels on the screen. But if you ask neural network, if you give it examples and you will ask it yes or no question, then it will understand what the question is. And now another question. For instance, I will ask you if the white and black pixels are even or odd, if the quantity is even or odd. You would count it quite fast if there were just a couple of them, and just like flight attendants on the plane count people with a clicker, otherwise they will not be able to count. And if there are millions of pixels, you won't be able to count it. The computer will just count it. If you ask a neural network to count it, it will never think, what question is it? You will give multiples of examples where black, for instance, black pixels are odd and white pixels are even, and it will never understand what you mean. So there are things that neural networks understand just like humans, and there are some other tasks that humans understand and neural networks do not understand, but the reasons are different. Maybe the main reason behind it is while one task is minor, is small size to define more or less, if you take a space of parameters like a million of parameters, million of pixels, more white or more black ones, it's very easy to understand it. And it's small size. The size of the task is one. And second, when you have a cube and it has a chess order, then anyway, it's the same task. Then there are different deviations here into biology and to neural networks. What humans can do is small size problems when we have an XGA screen with a million pixels and it's a huge space. But the structure that we're observing there helps us and bring it down to the size of a task of 50 or 100 maximum. And the same happens with neural networks. Maybe we need a language that describes small size geometric structures in multi-dimensional spaces. And our intuition is based on 3D, 3 dimensions, and neural networks have a different understanding, and there are more dimensions there. But I believe that most probably this is the point, how to there's just an equation that's one-line equation. We feel more comfortable when the size of the object that we're studying is less than 100 digits. If it's an equation one page long, then we not feel comfortable solving it. I began saying this, that in case if artificial intelligence imagines something and we improve computation power and the size that we can comprehend is 100 and it has computation power of 200, maybe it will come up with something new. It's a question. It's the most important question, exactly. I wanted to clarify one thing. It's referred to what Konstantin Sergeyevich also said. Physicists don't like tough or complex tasks, but if you create a language that's going to be so multidimensional, that is going to have a multidimensional million dimensions, so do mathematicians like complex tasks? No. I like small particles, small tasks, not simple tasks. It's a pure proof of it got stolen from me. Yes, I remember one publication that I had. One of my friends, well-known, he said, it's such a beautiful article, I want to steal it from you. But actually, we like simple tasks. We don't like complex tasks. We have the same goal. We share the same goal with mathematicians and physicists. We want to understand how it really works, and we want to understand how formulas describe it. But we also, those things that we're doing, we came up with some rules and why some beautiful things come as a result of the rules that we come up with. We don't know, and we want simplicity. We're striving for simplicity. The horizons of our knowledge, they are mesmerizing me, and I'm sure it's going to be a subject for more discussions. Konstantin Sergeyevich, getting back to physics. Physics set tasks for AI many times. It stimulated development of the industry. Their new mathematical models became available. Most important concepts in physics are applicable in machine learning now. I don't know whether Boltzmann machine is discussed now, but I'm sure that new grades, law, or recommendation systems become available. When we comment on your new lab of Moscow Physics University, you emphasize that new materials are required, but some non-trivial properties, for instance, to create neuromorph computers, I'm sure we're going to discuss them here as well, that will work just like our brain works. Also, importance of new materials to study interfaces with living objects, for instance, interface of computer brain. It seems that it's a great prospect for brain studies, but fundamental physics and physics of materials, how can they help studying AI today? Konstantin Sergeyevich, over to you. You are muted. We cannot hear you. You have touched upon a very interesting problem about neuromorphal computers Of course, we don't have a good understanding of how they work or how they're supposed to work. We don't think we know how neurons operate in our brain. We can just approximately imitate it in our machines or devices. But the problem is that these machines and devices will be extremely non-linear. And just like it has been said, just like Stanislav said, that when we receive something non-linear, we stop understanding it. We can't predict it. We don't understand it, and it's really difficult for us to coexist with it and to do something about it. These systems are not just not linear; they must have memory. As soon as we start speaking about memory-related systems, it immediately means that the system is not balanced. And physics currently is not equipped enough to describe it. We are trying to describe simplest balanced systems, and then we are disbalancing it a little bit and looking where is it going to move, how is it going to swing, how is it going to move back or swing back. This is maximum what we can do. Memory systems or memory-aided systems is a huge amount of tasks, and we're only approaching them. We have some systems that we know well. We're great at working with them. We're great at operating them. We know how to get memory imprints on them, and we hope that we will be able to create neuromorphal computers in the future. One of the problems with artificial intelligence is that it works well, it works perfectly fine, and we have a lot of tasks that can be solved with the help of AI. But the problem is that just try to plug it into your cell phone or connect it to your cell phone, and you will have problems. Because we're trying to solve significantly nonlinear, disbalanced tasks on our regular processors, regular CPUs that are just not designed for it. This is why creating materials and devices that have memory and you can use this memory, and brain is actually a device that contains memory. Our microprocessors, it would be great to have it in our microprocessors, and this is what many people are studying now. Phase-changing materials, materials with memory. This is a popular thing to do now. The problem is that, as I said, we don't have a way to describe these materials. We are describing materials only in a balanced state. And as a result, it's a vicious circle. We're using dynamic AI, those kinds of AI that live in time, that can describe thermal materials for us to develop computers. So as a result, AI is trying to compute itself and is trying to create a computer to recreate itself. And it's really exciting for me what might be the result of this. I can't even explain it enough. I don't have enough words. Oh, it's a mind-blowing idea. I'm so amazed by what you have just said. And by the way, using the opportunity, I wanted to say thank you to you for cooperating with Sberbank. to establish our scientific award, and you were on the committee that established this award. And we're about to conclude our cycle, and the next question is to Konstantin Vladimirovich. Oftentimes we hear that machine learning, modern ways of machine learning, they are not guided by biological models, but in the beginning, about 100 years ago, they were based on that. Canadian scientist Jamin Schiffer would say that these approaches are useful, but they will not have anything in common with artificial intelligence advancements, except for abstractions or motivations. When he illustrated it, he said something that was used by Stuart Russell and Peter Norrell. These were attempts to make people fly just like birds. It gives us a fundamental idea. It gives us an idea of wings, for instance, planes or aircrafts. They fly using different principles rather than those principles that birds are using to fly. However, artificial intelligence and science are closely connected. For instance, Thomas Sopoljo from MIT would say that science without a teacher is based on biological representation. If we know that biology can do it, then the question is only how to recreate it with computers. Konstantin Vladimirovich, I know that you have managed a number of projects, including at the Institute of AI in Sber. So how does contemporary neurobiology help make a breakthrough in AI creation? Actually, until we're doing it with the purpose to make a breakthrough, and it hasn't happened, and until it happens, we're going to keep on doing it. If we only knew what the breakthrough would be today, we would already have had it. As to connection between AI, of course, there is connection between neuroscience and AI. Marquardt was a neurophysiologist, and Rosenblatt was a psychologist. Jeffrey Hinton was a psychologist. DeepMind, to a large extent, is based on neurological research results. And the principles employed in aircraft construction are not the same as the way birds are flying. But on the other hand, there is a great room for what biological systems can do and what AI cannot do. I don't think we would oftentimes come across a case that a sparrow got crushed during landing, or a pigeon didn't have enough of a takeoff space. There's an intersection. Area is huge, and there are a lot of searches and research like this in the world. For instance, as Konstantin was speaking about memory. Memory is one of the obvious things that is expressed in biological neural networks and doesn't really work if we speak about technical AI networks. In artificial AI, it requires a lot of repetitions to memorize some things that must be memorized with the first attempt. On the other hand, there's something different here. Artificial intelligence can do some things that biological things are not proficient enough in. And there's an interaction. There's one project that we are beginning now with the Institute of Artificial Intelligence at Sber, and it is based on searching for these overlaps between artificial and natural intelligence. It began with one presentation. This presentation is going to be given today. It's about a memory system that helps establish connections between events that are widely distributed, that they're not connected, actually. Searching for connections is an important thing, but biological intelligence does it at a limited interval of time. Biological or natural intelligence can find connection between events that happened nearby to each other. like a few seconds, and for animals and for humans, it's difficult to establish cause and effect relationship between different types of signals. And artificial neural networks can establish cause and effect relationships through huge spaces and huge intervals in terms of time and space. This is what biological networks cannot do, but still it takes millions of repetitions. But in biological neuron networks, these connections of these cause and effect relationships takes just one attempt, just one time, and it doesn't require millions of repetitions. And neuron cells place two events into one department, and these events in the beginning were not connected, but they do have connection between them. So we can expand capabilities of association memory. On the other hand, we need to understand how associations are created on the go and how associated memory can be applied in neural networks, and I expect a lot of interesting discoveries here. Thank you very much. You know, this transformer race that you spoke about this morning, it began with a well-known article, "Attention is all you need," it's called. Maybe you or Konstantin Sergeyevich could jointly write an article that memory is all we need. Our time is almost up. Thank you all very much. And we have a lot of questions from our audience because the discussion is very interesting. I will choose just one question that was received from abroad. We have foreign guests who are watching us, and it refers to all our speakers. So I will ask you to please give a brief answer to this $1 million question.
Do you think it's possible to stimulate the brain with the current level of algorithm? And what is the biggest challenge other than computation power? Что сейчас является самым, есть ли у нас возможность стимулировать?
Is there a chance to simulate a brain with current algorithms, and what is the biggest challenge on top of computing power? Who wants to begin answering the question? Sergey. There is a Blue Brain project there in Switzerland, right? Yes, it's one of the two European mega projects, along with the material-related project that Konstantin is a part of. And the capital is between Lausanne and Geneva. And I'm not a part of it, but I spoke a lot to biologists and to those who are a part of this project. There are a lot of biologists who believe that what this project is promising is actually impossible to make. I think Konstantin knows more about it, and they have already modeled one of the cortexes of a mouse completely, and Geneva Lake is heating by 2 degrees when they're doing this, right? Yes, just like the point that they're doing experiments at night in order not to overload the power grid. It's not clear yet whether it's going to work, and if we're going to make a model, if it's going to explain something to us or not. It's like if I give you a blueprint of Pentium and it's the first time you see it, whether you will be able to understand what it's about or not. So it's an interesting question. I think it will have some benefit, but not the benefit that we expect to gain. Konstantin Vladimirovich. I belong to those biologists who are very skeptical about blue brain projects. I think it's bullshit. I think that copying or cloning all the brain cells of a mouse or a rat, it will not help us build human brain, but there are big data there, it's a big idea. We need a scientific breakthrough, and masking this idea with a lot of fuss about current progress, it only makes it more confusing. There's no point in bragging about it when there's nothing to brag about yet. Just like all fundamental things that refer to other properties of neural system, mind and intelligence, different kinds of brains and organisms have it, and sometimes they don't have cortex. For instance, birds, they don't have cortex, or those who do not have complex brain, for instance, some fish. This idea is not there yet, so I think this is what's missing, the algorithm. It's not the stage when we need an algorithm. Algorithm will become available at the next stage. Looks like we all are pessimistic here. Konstantin Sergeyevich, what is your view? I agree. I agree. I agree with Konstantin. The main problem here is that it's not about the capabilities that we have to simulate or computing power that we have. The main problem is that we don't know what we want to simulate. We don't have enough understanding of how brain works, and it's even worse than black box. It's even more black. We don't know what are the ins and what are the outs, and what's the input and what's the output, and what's the data that we are processing. So the task is so poorly defined that we can try and create some analogs, some similarities, but I believe that even our neuron simulators are not complicated enough, are not practical enough to really give some information about how brain really works. There will be some benefit as a result of it, however, at the point when we overcome some complexity threshold, I guess we will get a system that we will be able to advance significantly, go to a new level, and we will have an understanding of some major problems, and we will understand where to invest. One of the things that I will remember after this discussion is what you have just said. So the takeaway is that brain is even more complicated than a black box. So in conclusion of the discussion, thank you very much. I hope that everyone taking part in this Zoom, all the audience is gonna give a round of applause to all our speakers. Thank you very much for being here. Thinking about Game of Thrones and Tyrion Lannister, once he said that all human history consists of dialogues. So today we had a dialogue that will definitely go down the history of AI in Russia, go down the history of AI globally maybe, because we discussed very important matters, very important issues. We haven't found a solution, but we'll keep on searching for solutions. Thank you very much. We're having a small break now. Thank you. Thank you. Goodbye.